My name's Hawkins Gay. I'm an electrophysiologist at Northwestern Medicine, and I'm going to be reviewing some research that we did there a couple of years ago, where we tried to take 12-lead electrocardiogram data and predict. We were looking at atrial flutters, and we were trying to accurately predict which ones were atypical flutters, and then more specifically for the atypical flutters, were they coming from the left or the right atrium, because that's information that electrophysiologists care about. And it actually is helpful clinically if we're going to be thinking about procedures and ablations to know with high accuracy where that flutter is coming from. All right, so we'll get started. So I just like this slide. Everyone's always asking about the difference between statistics and machine learning, and then this lays everything out on a nice kind of Venn diagram here. But all of this is overlapping, and it all interconnects in different ways. And basically, statistics is underpinning all of this. And I just think that this is very helpful for a lot of people to see how these all interconnect. So at 50,000 feet, there are really kind of three primary types of machine learning training, and I'm going to be talking mostly about supervised learning today. And supervised learning is where you're training an algorithm with labeled training data to make accurate predictions on unseen observations. Again, this is kind of the supervised learning landscape. And again, this all exists on a spectrum, and it's separated on that spectrum by the amount of assumptions that the model makes about the data landscape, and also by the amount of engineering that goes into putting the data together to be taken by the model. I guess a GAN is not really a supervised learning model, maybe semi-supervised by the discriminator, but that doesn't technically fall in here. For people that aren't as familiar with this is kind of the basic workflow of a supervised model. You have inputs, and in medicine, this is usually some sort of clinical input. It could be data about the patient, or it could be the raw 12-lead electrocardiogram data. It's paired with feature weights. It gets passed through the model. Whatever architecture you're using, it makes predictions. You compare those predictions to known labels, and a loss function calculates an error. And then that error is used to go back and update the feature weights so that on the next pass through the model, it's going to be more accurate. For some models, like linear regression models, maybe there's a closed loop way of calculating the best feature weights, but for a large neural network, this is done in an iterative basis using advanced calculations like gradient descent and backpropagation. It can take hours or days to train large models in this way. This is another graph that I like. This was from an editorial written a few years ago, but it kind of gives an idea. When are you going to get more bang for your buck using machine learning versus kind of more traditional statistics? And I think a lot of it has to do with the data complexity. So if the data exists in multi-dimensions, or there's a lot of temporal and spatial features that are important to maintain, then machine learning may perform better. All right, so we'll jump into the case study now. Again, this is the question that we were starting with. Can we develop an accurate model with utilizing 12-lead electrocardiogram data only to help us differentiate typical versus atypical flutters? And more importantly, with our atypical flutters, can we accurately diagnose left versus right atrial flutters? So this is our workflow. One of our bottlenecks here is we need labeled data. So we have to know with high accuracy whether the flutters that we're putting into the model are truly atypical, and are they truly coming for the right or left atrium. So we needed an ablation to have been done. Northwestern switched over to Epic in 2017, so we went through all of our ablation reports in Epic. And we were able to find about 1,300 ablation reports that accurately kind of labeled our flutters. Unfortunately, about 400 of those patients didn't have an ECG of their flutter in the Muse database for us to use. And a little over 200 had multiple flutters ablated, so we couldn't say with accuracy, even though we had the ECG, where the flutter was coming from. So that left us with about 700 electrocardiograms to use in the model, and well over 500 of those were typical flutters. So we had, one of the limitations here is we didn't have a lot of data for the atypical flutters. Then the next question is, all right, well, I showed you a bunch of the models. What's the best model to use for this question? Around this time, these deep learning neural networks were achieving state-of-the-art performance with signal analysis and digital analysis. So that's what we initially started with. I mean, everyone's seen this now. A deep learning neural network just means that you're using a neural network that has 4 or more hidden layers. And those hidden layers are what everyone's been talking about as the black box. A convolutional neural network is an important type of neural network to know about, especially when dealing with time series data or imaging data. And it's really used when you have data that has important spatial and temporal interconnectedness, because the feature maps that are created during the convolutional aspects of the model are what maintain that relationship. Ultimately, they're flattened and put into a feed-forward network, but it's a very useful type of modeling for a question like this. And so these are our early attempts to classify this with a convolutional neural network, and our initial attempt was terrible. I flipped the axis here, so it should be predicted on top and actual on the x-axis. But what was happening is we had really unbalanced training data. We had 5 times more typical flutters, and the model, we didn't balance it initially, and the model just learned to predict everything as a typical flutter. When we went back and balanced the training data, it actually tried to make predictions about atypical flutters, but it still had really low accuracy. And I think, the biggest problem here is that we had a limited amount of data, and these, large models have millions of parameters that need to be fine-tuned in an iterative process. And if you have a couple hundred examples, you're not going to be able to accurately fine-tune this always. There may be some scenarios where it works okay, but it didn't work out well here. So then we had an idea, well, why don't we try something called transfer learning? And transfer learning is a process where you can train a model on a task that's similar, but not the exact task that you want it to perform at the end of the day. You use the same architecture and the same number of parameters, just not the same initial question. And then you transfer those, trained weights that are trained on a similar question to the final model, and you just fine tune it with the limited data that you have, and hopefully hopefully you're starting like halfway up the learning curve or 3/4 of the way up the learning curve, and it'll perform better. So what we did is we built a model, a convolutional neural network that could recognize just atrial flutter from not atrial flutter. And here we weren't bottlenecked by needing an ablation report. So Northwestern has millions of electrocardiograms in its Muse database that has been read by a cardiologist to be atrial flutter, and millions that haven't. So we just downloaded about 20,000 of each and had a balanced data set, and we trained a model that can accurately predict atrial flutter with high accuracy, high precision, and recall as well. And then we initialized our model with these weights and fine-tuned it with the limited data that we have. This is the architecture of the model, just as an example. Even a relatively small convolutional neural network like we utilize has over 2 million parameters that needed to be trained. And it improved our accuracy. It was about 87% when we used transfer learning, but still we were hoping for something north of 90 and really north of 95%, and we were not getting it with deep learning models. So then we went back to the drawing board and we said, okay, well, we have to choose. Let's try a different model. What models are available to us? Now I'm separating things, in a parametric versus non-parametric model. Parametric models are making assumptions about the data landscape. Is it a linear model? Whereas non-parametric models kind of learn the landscape in a way as part of their training. They don't make any inherent assumptions about it. So they're better with complex data and high dimension data. People may not be as familiar with these, so I'll run through them quickly, but K-nearest neighbors is a class. It's often called a proximity classifier, and it's pretty simple what it's doing, especially if you're looking at it on 2 dimensions like this. It has the labeled training data. Here we have our triangles and our stars, and then you put a new data point on the field, and you tell it to utilize the nearest neighbors and however many dimensions there are and classify it in some way. So if you choose K equals 3 nearest neighbors, well, it says, okay, 2 of the 3 nearest neighbors are triangles, so I'm going to classify this as a triangle. If you tell it to pick 7, it says, all right, well, 4 of the 7 are a star, so I'm going to pick a star. And so that's basically how this algorithm works in very simplified form. A support vector machine, also known as a large margin classifier, again, in a very simple format here, 2 dimensions, is trying to find the optimal hyperplane or line in 2 dimensions that separates the data. You can see a bunch of possible lines on the left, but the optimal line for a support vector machine is the one that has the largest margin between the data points. And this doesn't have to be linear. They're kernelized support vector machines that can model a nonlinear pattern, and especially in multiple dimensions, you get a hyperplane. And whatever side of that hyperplane the new observation falls on, it'll be labeled in that way. And then this is a decision tree. It's maybe the hardest to explain. This is one that was built with a very popular data set of Titanic passengers. A lot of people, compete to try to predict accurately which Titanic passengers are survivors and which one's deceased, but it makes for an easy explanation. And so this decision tree is using 3 pieces of information about these passengers. What class were they traveling in? And that gave the model enough information to accurately classify first-class passengers as survivors and third-class passengers as not surviving. Second-class passengers, it needs more information. If you give it gender, it can accurately, predict that females in second class will be a survivor, but with males, it still needs more information, so you give it age. And then finally, you cross a predefined threshold, and the model says, okay, now I have enough information to accurately predict, every new observation as a survivor or not. The way that you put nodes into the decision tree ideally is you want to pick nodes that increase your or have the maximum amount of information gained first, and there are ways of calculating that we don't have enough time to talk about. Ensemble learning is another powerful way of basically trying to combine multiple models and make more accurate decisions. It's kind of like wisdom of the crowds. It allows you to kind of minimize bias and variance. And there are a lot of different ways of doing it. You can train models in parallel. You can do sequential modeling or stacking, and I'll show you some examples of this. But this is a popular modeling method called random forest. And what's happening here is you have 3 decision trees, like I just showed you, again, trained on the Titanic data set, and they're making predictions in parallel. And 2 of the 3 predict that the passenger survives, and so the final outcome of the random forest is going to be that the patient survives. So back to our question and back to our modeling effort. So what we did is we built a stacked classifier, and we utilized random forests, and that was able to act. And this is for the first question: is this a typical versus atypical flutter? And it achieved classification accuracy of 88%. Support vector machines got 94%. K-nearest neighbors had impressive accuracy of 95%, and then if you stack them in soft voting, you get great accuracy of 98% with high precision and recall for typical versus atypical. And then if you run the atypicals through a similar ensemble, we were able to get an accuracy of 95% with precision and recall of over 90%. This was, published in a paper that we looked at, and we also externally validated it with data from outside of Northwestern, and it performed again with not quite the same accuracy, but over 90%. And so just kind of in conclusion, I think we learned a lot from this, but again, I do think choosing the right model for the data that you have is really important. There are really advanced models out there that people are doing great things with, but you may not have the right amount of data or the time or the manpower to train those types of models. But there's a lot that you can do with more limited data, and you don't always need to use the most advanced machine learning modeling out there.